Imagine a single teaspoon of material so heavy that, here on Earth, it would weigh as much as a mountain. About 1 billion tons balanced on a spoon. That substance is real. It is what neutron stars are made of, and they are among the strangest objects the universe has ever built. To make one, you first have to destroy a star. When a massive star, many times heavier than our sun, runs out of fuel, its core can no longer hold itself up. In a fraction of a second, it collapses, and the outer layers crash down and rebound in a titanic explosion. A supernova. The explosion tears the star apart, but at the very center something is left behind. The collapsed core, squeezed by unimaginable force, survives as a tiny, dense remnant. If it is not quite heavy enough to become a black hole, it becomes the next strangest thing, a neutron star. The collapse is so violent that it overwhelms the very structure of matter. Normally, atoms are mostly empty space, with tiny electrons orbiting far from the nucleus. Here, gravity crushes the electrons down into the protons, and they merge, leaving behind a sea of pure neutrons packed together. That is where the name comes from. A neutron star is almost entirely an enormous ball of neutrons, the same particles that sit inside atomic nuclei, but here piled together by the trillion, on a scale no nucleus ever reaches. It is, in a sense, a single atomic nucleus the size of a city, and the scale is the first shock. A neutron star packs more mass than our entire sun into a sphere just 20 kilometers across, about 12 miles. You could drape it across a single city, all the weight of a star, crushed into something you could drive across in 20 minutes. Cram that much mass into that little space, and the density becomes almost meaningless to imagine. A sugar cube of neutron star material would weigh more than all of humanity combined. The matter is packed as tightly as the particles inside an atom's nucleus. It is nature at its most extreme. With all that mass in so small a ball, the gravity at the surface is staggering, hundreds of billions of times stronger than Earth's. A marshmallow dropped onto a neutron star would hit with the energy of an atomic bomb. Nothing we know could ever stand upon that surface and survive. That gravity flattens everything. A neutron star is one of the smoothest objects in existence. Its crust is solid, far stronger than steel, but the gravity is so fierce that the tallest possible mountain rises only a fraction of a millimeter. A world polished almost perfectly round. Now make it spin. As the giant star's core collapsed, it sped up, the same way a skater pulls in their arms and whirls faster. A neutron star can rotate dozens, even hundreds of times every second. A city-sized ball, heavier than the sun, turning faster than a kitchen blender. Many neutron stars beam radiation from their magnetic poles. As the star spins, those beams sweep across space like a lighthouse. If one happens to point at Earth, we see a pulse, regular as a clock, flashing many times a second. We call these spinning beacons pulsars. These pulses are astonishingly regular. Some pulsars keep time so precisely that they rival the best atomic clocks on Earth, ticking steadily for millions of years. When we first detected one, the signal was so perfect that, for a moment, some wondered if it was a message from another civilization. Some neutron stars hide an even fiercer secret. A rare kind, called a magnetar, carries the most powerful magnetic field known to exist, trillions of times stronger than Earth's. It is so intense that, up close, it would scramble the atoms in your body, unraveling the very chemistry that holds you together. The crust of a neutron star is under colossal strain, and sometimes it cracks. The surface shifts by perhaps a millimeter, but with such force that it releases a burst of energy beyond imagining. From a magnetar, a single such starquake can briefly outshine everything else in the galaxy combined. In 2004, a starquake on a distant magnetar sent a pulse of energy across 30,000 trillion miles of space, and it still disturbed our atmosphere and our satellites here on Earth. A tiny crack on a faraway star felt across the entire galaxy. And beneath that solid crust, we are not entirely sure. The cores of neutron stars are denser than anything we can recreate or fully understand. The matter there may flow as a frictionless superfluid or be crushed into forms of matter that exist nowhere else. The center remains a genuine mystery. That superfluid interior would behave in ways that defy everyday sense. Once set spinning, it would swirl forever without slowing, and it may store and release rotation in sudden jumps that we can actually detect as tiny hiccups in a pulsar's otherwise perfect timing. The inside speaks to us through the clock. The most spectacular fate comes when two neutron stars orbit each other. Over millions of years, they spiral closer, whirling faster and faster until they finally smash together. The collision is so violent that it shakes the fabric of space itself, sending out ripples we can now detect on Earth. Those ripples are gravitational waves, predicted a century ago and finally caught in our instruments. When two neutron stars merged, we felt the tremor of it pass through the Earth, stretching and squeezing every atom by less than the width of a proton. We had heard two dead stars collide, and the collision does something wondrous. In that instant, matter is blasted out and forged into the heaviest elements in nature. Gold, platinum, the rare metals of the Earth. A single neutron star merger can create more gold than the mass of many planets, scattered glowing into space. Let that settle in. The gold in a wedding ring, in a buried treasure in the circuitry of your phone, was very likely forged in the collision of two neutron stars, long before the Earth existed. You are wearing the debris of one of the most violent events the cosmos can produce. For days after such a merger, the scattered debris glows with the light of radioactive heavy elements, an afterglow astronomers call a kilonova. We have watched one fade across the sky, reading in its light the unmistakable fingerprint of freshly minted gold and platinum drifting outward. Neutron stars live on a knife's edge. They are the densest objects that are not black holes. Add just a little more mass, push them past a certain limit, and even neutron pressure fails. The star collapses the rest of the way, and a black hole is born. They sit at the very brink of darkness. For something so small and far away, neutron stars are surprisingly loud. We find them by their radio pulses, their X-ray glow, their starquakes, and now the gravitational tremor of their collisions. Across the spectrum, these tiny corpses of giant stars are constantly announcing themselves to anyone listening. Each neutron star is an experiment we could never run on Earth. They test matter at densities and magnetic fields far beyond any laboratory, under gravity that warps space and time. To study them is to read the results of experiments the universe runs for us, in conditions we can only dream of reaching. Some of these stars will keep spinning and pulsing for an almost incomprehensible span, ticking steadily long after their parent stars are forgotten. We have even imagined using their perfect rhythms as cosmic signposts, a way for future travelers to fix their position anywhere in the galaxy. It is a strange kind of immortality. The giant star dies in fire, but its crushed heart lives on for ages, spinning, flaring, forging gold when it collides, seeding the galaxy with the raw material of worlds and rings and circuitry. Death here is astonishingly productive. So hold the whole picture for a moment. A city-sized ball, heavier than the sun, spinning hundreds of times a second, wrapped in the strongest magnetism in nature, smooth to a millimetre, and 1 teaspoon of it heavier than a mountain. Every word of that is true, and it is out there right now. And it is not so distant from you as it seems. The heaviest atoms in your body and your world were born in the deaths and collisions of these stars. To understand a neutron star is, in a small way, to understand where the most precious pieces of the Earth actually came from. The next time you read that a star has died, remember that its ending may be a beginning. Somewhere out in the dark spins a tiny, impossible ember, denser than thought, brighter than reason, quietly keeping time and forging treasure, a spoonful of which would weigh as much as a mountain.